In this video, we will learn about a special type of matrix in which all entries are same, and we will find all these written here for that matrix. And if you are aspiring for CSIR net, then you have to analyze how to think when such a problem appears in your exam, so that it takes at most 1 minute in the exam hall. So let us first consider a matrix of size 3 of such type, and then we will generalize it for matrix of size n. Well, this is a matrix of size 3 where all the entries are same. Now, without solving the characteristic polynomial for this matrix, can you say what are the eigenvalues? Well, I can claim they are 3a, 0 and 0. How? See, these two column vectors are linearly dependent. So one eigenvalue must be 0. Why? Because since these two column vectors are linearly dependent, so the rank cannot be 3, which is the order of this matrix. So the determinant must be 0. So at least one eigenvalue must be 0. And also we have a result that says this: if the sum of all entries in each row is same, then that row sum will be an eigenvalue. Here row sum is 3a, 3a and 3a, so 3a must be one eigenvalue. So now I am deducing that the third eigenvalue will also be 0. Well, we will come to that later, but to understand why this row sum thing happens, what is the analysis behind it? See, if this is an eigenvector, see, it will be what? A into x plus y plus z, a into x plus y plus z, and a into x plus y plus z. So it will be what? A into x plus y plus z into 1, 1, 1. Now here, if we put x is equal to y is equal to z is equal to 1, then it becomes what? All the entries are same in this matrix, and 1, 1, 1, it will give 3a into 1, 1, 1. So 1, 1, 1 becomes an eigenvector, while 3a is an eigenvalue. So if the sum of all entries in each row is same, then that value will be an eigenvalue, and 1, 1, 1 will be the corresponding eigenvector. Now come to that question, why the third eigenvalue is also 0? Well, it is quite easy. If the third eigenvalue is lambda, then lambda plus 3a plus 0 will be trace of this matrix. Trace of this matrix is what? 3a. So lambda must be 0. So we have found the eigenvalues and their aims, and eigenvector corresponding to 3a. Now we have to find the eigenvector corresponding to 0. Now see, let us write this matrix again. If x, y, z be an eigenvector corresponding to 0, then it will be what? I am not writing this again because we have already calculated this here. So if x, y, z be an eigenvector corresponding to 0, then it will become what? This vector will be equal to 0. That means this will be equal to 0, 0, 0. Right? Then we have only one equation. From this whole system, we can have only one equation, which will be what? X plus y plus z is equal to 0, because provided a is not equal to 0. So z can be written as minus x minus y, and that is why x, y, z can be written as x into 1 0 minus 1 plus y into 0, 1, minus 1. So now the system of this equations reduces to only a single equation only because of the properties of this matrix, because all the entries are same. Now we know that the kernel for this matrix is equal to the eigenspace corresponding to 0. Why? Because we know that eigenspace is equal to x such that if we consider this matrix as Ax is equal to lambda x. Here lambda is equal to 0, so E0 will be the kernel. So E0 here is 1, 0, minus 1 and 0, 1, minus 1. And E3A will be equal to what? Will be generated by 1, 1, 1, as we have noticed here. So we notice that the geometric multiplicities for 0 and 3A will be 2 and 1 respectively. But if you want to apply some results or use some shortcuts, then here are some. Now to find the GMs easily, we will apply node 2 and node 3 and see this matrix is symmetric. So we can easily apply node 3. And since we have already deduced that the AM of 0 is 2, and since this is diagonalizable because it is symmetric, so GM of 0 will also be 2. And similarly, the GM of 3A will also be 1. Thus, we have found the GMs also. And eigenvectors and eigenspaces also. Now to find the minimal polynomial. Since we know that this matrix is diagonalizable, so we will apply another node, this one. So we conclude that the minimal polynomial for this matrix will be what? X into x minus 3a. Now to generalize all these for some n order matrix, we have the eigenvalues for this n order matrix as NA and 0, 0, 0 n minus 1 times. So the AM of 0 is n minus 1. GM of 0 is to be deduced later. AM of NA is 1. GM of NA is what? 1 again. Why? Because this is symmetric matrix, so it is diagonalizable, and that is why AM is equal to GM. By similar approach, we can say GM of 0 is n minus 1. Now to find the eigenspaces, if we proceed in a similar manner, we see that the eigenspace for 0, E0, is generated by 1, 0, 0, 0, minus 1, 0, 1, 0, 0, 0, minus 1, and so on. And the last one is 0, 0, 1, minus 1 is generated by this type of matrices, vectors. And E of NA is generated by what? By a vector with all entries 1. And the minimal polynomial for this matrix will be what? X into x minus NA. X minus NA. This will be the minimal polynomial. So this is the generalization for this type of matrices. Thank you for watching. Don't forget to subscribe.